I'm finished my cooking.
Good afternoon, everybody. We're going to go ahead and start. It is my great pleasure today to welcome our honorary guest, Professor Patrick Jaillet from Massachusetts Institute of Technology. He's here as part of our Wasserstrom Family Distinguished Lecture. The Wasserstrom Family Endowment provides support for activities that enhance and supplement the educational experience of the Industrial Engineering Management Science Department. And as part of that, we have our annual Wasserstrom Family Distinguished Lecture. Alan Wasserstrom is a graduate from 1962 from our department. He's very actively involved with the department still as the active advisory board member. He is also a Distinguished Alumnus Award winner, and he's currently the owner and CEO of the N. Wasserstrom and Sons Company. So we acknowledge and grateful for their support for this type of activities. Now, Professor Patrick Jaillet is coming to us from Massachusetts Institute of Technology. He's the Dougal C. Jackson Professor in the Department of Electrical Engineering and Computer Science. He's also a member of the Laboratory for Information and Decision Systems at MIT, as well as one of the two directors for the Operations Research Center at MIT. He completed his undergraduate studies in France, and then he moved to Boston to get his master's in transportation and PhD in operations research from MIT. He was a Fulbright scholar from 1990 and has numerous awards, which will take me the next 50 minutes all to list, but I wanted to highlight a couple. He most recently received the Glover Kligman Prize, and he's also the newest fellow of the Informs, our professional society. And they recognize him as a fellow for opening the field of a priori optimization for stochastic programming and for being regarded as the world leader in the field of probabilistic and online optimization. So without any further delay, I would like to welcome Professor Patrick Jaillet, and looking forward to learning about routing optimization with uncertainty.
Thank you very much for the kind invitation and the kind words. I don't deserve that. So now, I typically, when I give talks, I move a lot, but I've been told that I should not move because I'm stayed there. So I might stay still or stiff or whatever. So when I received the invitation about 6 months ago or something like that, I said, yes, great, thank you very much. And initially, if you look back at what I'm doing in terms of research, I've not been doing a lot in transportation, actually. I've been doing a lot now in online auctions, data-driven optimization, and things like that. And we had a recent project on kidney exchange program and the use of dynamic bipartite matching there. And I thought that maybe this is what I should talk about. But then Karen sent an email to me saying, yes, someone is invited to talk about transportation. So I was like, oh, okay, so let's talk about transportation. Karen was actually invited to come to MIT last week, and she was giving a talk as well. And there were a lot of people in the audience. It was an ORC seminar that came from the civil environmental engineering, from the transportation group, because they thought that Karen was going to talk about transportation. And she talked about healthcare instead, but that's okay. All right, so let me start. I was not sure about the audience in terms of technical, how should I make it, technical or not technical. So I'm trying to, so the best actually would be for you to interrupt me whenever you want to get more details about what I'm saying, because in some sense, I've removed some details from it so to make it more manageable in some sense. So before I move on these, even though I've not worked a lot in transportation, this has been revived with this grant that we had from Singapore. It's a very large multi-PI grant from MIT. We are 10 MIT PIs on it over 5 years, and the program started in 2010. And the title is Future Mobility. And for us, if you look at the 10 MIT PIs, I think 2 faculty are really in traffic, really specialists of transportation, like Moshe Ben Akiva. I mean, really, that's their field. And many of us are more on the tangential side, and a lot of my colleagues from EECS, where we were just interested in looking at developing new algorithms that would take advantage of all this huge amount of data. And so it brought me back to some topics that I had studied way back in terms of optimization, both the traveling salesman problem, but also shortest path. So that's the background. But with a different twist, I realized that many of our models that we had in the past didn't really apply, so we wanted to do something different. So that's what I will be talking about. Now, this is, as many faculty know, when they turn being very old, like I am, most of the work is done by postdoc and graduate students. And so Yossiri was a postdoc that was with me for about a year. He graduated from Montreal, and essentially I would say is a large-scale optimization, integer programming type of guy, and also cuts and cuts and cuts. So he was very useful for me. Arthur Flageolet just started. He came from France. He was at École Polytechnique, so I would say he's more like a mathematician somehow. But he just started, and he's at the ORC. Jin Q is a PhD student from NUS in Singapore. They just finished as well. And Melvin Sim is a colleague. He was an alum from MIT, one of our brightest operation research center graduate, and is a faculty at NUS. So whenever I go to Singapore, which is quite often, I work with him. And so some of the work is with Melvin. Okay. And I didn't even put robust, but there will be some robust name in there at one point. All right, so that's the background. All right, so here is the outline of what I would like to achieve. And I'm going to go back to routing on networks under uncertainty and just motivate very quickly what we want to look at in these problems. Then I will have two parts. The first one is dealing with what I call a priori solutions, solutions where you have to find solutions on network that are before realization of any kind of uncertainty, and you don't modify the solution, you just get it. So that's why I call a priori. And the other one are more classical adaptive solutions where you move along and as the network evolves. I would say like 3/4 of the talk would be here and only a little bit on this one. The reason is that this is the most recent work, and even though it's not, it might be very interesting as well, I have less result to talk about. But all what I'm going to talk about is very recent. So we have either working paper in the revision submission or that are about to be submitted. So I would say 2013, 14. So it's pretty fresh in terms of what we're going to talk about. But for those of you that are interested, I have essentially the working papers on my webpage, or I can send it to you if you are interested in looking more at details. All right. In terms of overview, the real, I think I would have achieved my goal if I can convince you about one thing, about a new performance measure that we're going to introduce is a very interesting performance measure. And I'm going to spend quite a bit just talking about that, going through very simple example. And all the rest might go very fast, might be more like math in there, but really what is critical is to understand why we have introduced this new measure, right? And why, because it's not entirely obvious why this measure makes sense, right? So we're going to spend some time there. All right. No questions about the introduction? Okay. All right, so motivation, pretty simple. The motivation actually that interested me to go back to this kind of problems is this one. And the motivation is not really an academic motivation, it's really to develop iPhone app. So it was very practical, and we were working at that time with Google. You all know Google, right? So you took things, you want to go from A to B. At one point, you had only one solution given to you. Now you have 3 solutions. So that whenever you took one and it works out that it's not the good one, you blame yourself, not Google, right? That's the first marketing tool that you know. Now, all these things are based on real-time data, right, and crowdsourcing, but nothing about prediction. They have no predictive model in there. So it's just that it gives you the real world now, not in 5 minutes, not in 10 minutes. And so this is what we wanted to do is can we do the same kind of thing, but also add some prediction there. And in many of these problems, what you want to do is solve shortest path problems. And shortest path, a lot of shortest path, and very often, and large-scale shortest path. So the key thing was to look at problems where you can do that very efficiently, very fast, and would take into consideration uncertainty. Right? So here, the basic issue here is to develop something not for the city that would try to remove congestions, or not for a company that would like to make business out of it, is just for a user to navigate better. So what we have in mind here is a user that likes to get some information, useful information. The other one is the more business application. In other words, there is the more classical, I would say, like vehicle routing type of problem, where you have the same kind of constraints there, but you want to route your vehicle to meet some of your customers' time window. And here, really what people are interested in is not to save time in terms of cost of routing, is really to make sure that whenever they say, I'm arriving at that customer between 10 and 11, they go there between 10 and 11. And the problem is, of course, is that you have a huge amount of uncertainty, and how do you develop trajectories, or how do you develop strategies where at least you are robust with respect to this uncertainty? All right? So these are the two motivations, but the big one that motivated me the most was this one, because this one involved very large scale, and it had to be so fast and almost in real time and often. All right, so now if you look at this kind of application, and if you look at shortest path in networks with uncertainty, there is a huge literature, right? And it goes back, so I've listed here some of it. And here I've listed, so the year where they have been published. I've omitted many, but I just put a couple along the way. I've indicated here if the approach was try to find a path a priori, a good path, to be defined how, or if it were adaptive. In other words, you're not defining a path, you write a policy where you move in a network and you make policy. So it's not a path. It's a, but then also what kind of network problems. So most problems are static in a sense that there is not time varying cost dependent, but few have introduced as well time varying, right? Then you hear the deadline restrictions, here the kind of uncertainty description. So in other words, what does that mean that you have uncertainty? Do you assume that there is a priority distribution? Do you assume the full knowledge of the priority distributions? So most of these papers here assume that. Few early on, Louis, for example, were thinking about a problem where you don't have the full distribution, you just have some moments, right? And but anyway, so these are a list of problems. I didn't highlight these two just because they're better than others. It's just because I'm going to talk about these, right? So I'm sorry, my name are associated with it. This is not proper, but that's how it is, right? So here, the key thing that I want to spend a lot of time is this notion of index-based new criteria that we have, and this notion of ambiguity, why I call it ambiguity. And we don't call it robust anymore, but all right? So that's the background in path problems under uncertainty. Huge amount of work. The key thing that we will highlight is that the shortest path problem by itself is a very easy computational problem to solve, right? P. As soon as you put any kind of measures here, you turn this very easy problem is an NP-hard problem. So typically what people have done is you formulate it, you say it's NP-hard, too bad, then you go to heuristic, right? But that was in 69. We have made huge progress where even NPR doesn't mean anything. You still have to solve that, and you want to solve that exactly. But what we are introducing here, this index-based, you're going to see that this is the only formulation that is still remaining polynomial. That's why the interest for us is there. All right? But so I'll give it a heads on about what we are doing. Now, in the area of vehicle routing problems under uncertainty, also there you have a lot of previous literature, uncertainty either in the demand, in the customer requirement. Here we have listed only those that deal with, again, travel time, stochastic travel time. But these series of works, what kind of network, what kind of sub-problems, Was it a traveling salesman problem type? Was it a vehicle routing problem types? How many vehicles do they have capacity, and so on and so forth. And here the kind of approach. So again, we're going to talk about these two here in that area. All right? All right. So now that we have that, let's define properly the kind of problem that we are interested in. Right? So the problem is the following. You have, as an input, you have a given directed network. Right? So we assume that we know all the network. You know the arcs. The fact that an arc is there, you know. Right? There is no issues there. Some of these nodes in these networks represent customers or represent destination, and there are time windows associated with it. So nodes here are customers, right? So I call them nodes now. And then you have uncertain arc travel time. That means that you have no certainty about the time it takes to go along that arc, right? Then the requirement is the following. Each node that has a time window has to be visited. And the arrival times at these nodes should respect time windows. I didn't put must respect time windows. As soon as you put must respect time windows, you give up, you close the book, and you say it's not possible. So should, right? Because, and now the output is that we want an optimal, I put a quote-unquote, routing strategy, quote-unquote, because we have not defined what criteria we want to use, right? So what are the challenges there? So these are the three challenges that we wanted to address. First, uncertain travel times. What does that really mean? How uncertain is it? Again, in my previous life, and I mentioned that today again with some of the students, as soon as I heard uncertainty, for me it was probabilistic assumption, stochastic model. Uncertain, I have a model, I take a random variable, I have the probability distribution, maybe there is some parameter to estimate, but for me uncertain meant probability. And then at one point I had a crisis in my life, and uncertain, no more probability. I wanted to solve against the worst case. So it was all the technique of online strategies, min-max strategy. You plan something that is robust against any kind of uncertainty. You don't make any assumptions. And now I'm coming back and bringing the two and say, well, maybe it's useful to use some probability there, but you don't have all the information. So the question is how uncertain, and we'll see here that how we're going to define that. As soon as you have uncertain travel time, what performance measure do you choose? And then the thing is that we want to have tackle large-scale size problem, right? So formulating something that mathematically is nice, if you cannot compute it, that's not useful. All right? That was the three requirements that we had put ourselves in. All right, so let's look at the first part of our talk, which is a priori solutions. So we're going to now, the assumptions and notations about the problem. The solution that we are interested in is an offline. So in other words, whatever uncertain things that you have about the network, while you are in a network and you learn something new, that something new does not give you any additional information. You stick to the previous plan. Or maybe that was the planning, maybe you changed, but what was interesting was the initial plan that you wanted to talk about. We're going to assume a classical shortest path problem. It's a single traveler. There is an origin. It starts from here, a destination here. And then you have this Cij tilde uncertain travel time of arc ij. And here I'm interested in a deadline at node, tau I being a deadline. And I'm going to assume first the first problem where you want to move from 1 to 6, and there is a deadline at 6. So think about you need to go to the airport, and you need to be there by 10, right? So trying to find the minimum expected shortest time doesn't mean much. You want to be there by 10. And what people thought about is, well, in terms of performance measure, if I have a lot of uncertainty and make some modeling assumptions about using probability distribution, I might look at the probability of arriving on time. And I might say, well, I want to maximize the probability of arrival on time and finding the path that maximizes the probability of arrival on time. This is exactly what the first author here made initially in '69, right? So that was essentially the formulation that is still looked at. All right? So that's the. So now let me discuss some of these measures. So this maximizes arrival probability. So that was the first proposed that. Very quickly, it ran into trouble, but I would like to just give you an idea of why there are some issues with some of these measures. So this one, there is a normative issue, and we all know that. Essentially, it ignored the lateness level, right? So what does that mean? That means that you're going to find the path that maximizes the probability of arriving on time. What that path does when it does not arrive on time is irrelevant in this criteria, right? So you can have a very fat tail in some sense, right? So a typical example that you can think about is you take these two paths, right? So, by the way, again, this is not convention in probability to use this t and tilde to represent a random variable. Typically, we use a big X or big Y. But since here, we're not sure if we are using probability distribution or not, this is the notation that we're using, right? But clearly here, this is a random variable. So T1 tilde, it takes 10 minutes with a probability 0.98, 20 minutes with a probability 0.02, and the other path takes 10 minutes with probability 0.99, and 100 minutes with probability 0.01. And the deadline, in other words, you want to arrive there by 19 minutes. Which path would you take? You would take this one, right? Most people would calculate that, even if you have no understanding of that probability. And and I've worked with probability. I still don't know how to make decisions with probability. So taking an expected value might be a variance or whatever. But this criteria here would take this one, right? Because 0.99 is bigger than 0.98, right? So this is what this model would pick. It would pick T2 tilde, right? So that's what I call a normative issue here, right? So there has been another popular, much more recent kind of criteria, and that is called maximize the punctual ratio. So the idea here is relatively simple. This is the deadline, so this is the expected time of your path. You take the difference between tau and that. Now, if the expected time is bigger than the deadline, already should give up on that path, right? But let's assume that at least it's smaller. You take that, and now you look at if there is a distribution variance. You take the standard deviation and you divide by that, right? So essentially, it says it's going to favor things that are much smaller than theta because I'm maximized. And also, since I'm dividing by the standard deviation, it will favor the path that do not vary much. So it's a very natural criteria, and we'll see that why it's also very natural and why people are using it. Now, the problem with this criteria is that it violates monotonicity entirely, right? And so here is an example. So you take that path with 10, probability 0.7 takes you 10 minutes. Probability 0.3 takes 20 minutes. And this one is 20 and 23, right? So which one would you take? This one is always smaller than that. Here, T1 tilde is less than or equals to T2 tilde with probability 1, right? It's always better, no matter what, right? Now, if you take this criteria and you apply it with a deadline of 22 minutes, it will pick this one. This is what I mean by violating monotonicity. You have two random variables. One is much better than the other one. Still, that is an issue. Now, if you continue on these two models, let's assume there were no normative issues. They were making things that were making sense. How hard is it to calculate the exact problem associated with maximizing the arrival probability subject to a shortest path or maximizing the punctual ratio? So for this one, for this problem, now this is for the shortest path, so that's why I had to define exactly what the shortest path is, because so far I was talking in general. But here, calculating this maximized probability is already hard to evaluate the objective function. Right? So just calculating for a given path the probability of arriving on time for that path with this convolution, if they are independent, or it's already a very hard problem to solve. So just evaluating a solution. And solving the problem is intractable. It's intractable in the following sense. You cannot even approximate it to epsilon. So it's an NP-hard problem as well. The problem with that also is that it does not allow what I call distributional ambiguity. And what does that mean? That means that you have to make an assumption about P, right? It's under a given priority space. And if you say the priority space P that I have, actually I don't really know what P is. P belongs to a class. That doesn't apply. You would have to use for P, you would have to find a solution. For P prime, that would be another solution. You cannot link the two. For this one, it's very easy to evaluate the function. Calculate the expected value of a sum of random variables tend to be very easy. Standard deviation, if you assume independence, it's very easy as well. But the same thing, the shortest path is intractable for that problem, right? Now, why was this one used and introduced? These folks, it's a very good paper, show that if you're under normality condition, so that means that the travel time on arcs are normal random variables and they are independent of each other, this criteria is the same as this one. In other words, solving for this problem would solve this problem. And for 30 years, people were trying to solve this problem because this problem is very, very hard to solve. So people made some assumptions and said, well, if you look at that criteria, it approximates this one. And by the way, it looks very natural. So that's why people spend a lot of time on there. And there are a lot of heuristics and algorithms looking at that. Now, it has an advantage is that, yes, you have a distributional ambiguity here. You can define a value, expected value, according to the worst case. So for this one, you have at least some distributional ambiguity. You can introduce ambiguity in the distribution and still have a framework that makes sense. All right. So now let's go to the framework that we're going to introduce. And unless there are questions so far. I've been very slow. Okay, so now let's go to this one. And for these ones, if you have done anything in economics or finance, it's going to be easy to understand at the beginning. So first of all, whenever you have a random variable, there is something called certainty equivalent, right? And this is defined like that. So you're given a parameter alpha, right? It's a risk tolerance, right? It's a given number that is called risk tolerance. And you replace a random variable like that by a certain quantity that is simply this measure here. Now, if you look at this equation, if the alpha goes to 0, right? In other words, your risk tolerance is very, 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 very small. That number here, these things, goes to the sup of the random variable. Okay, so in other words, the certainty equivalent for you, if you have a risk tolerance that is very, very small, essentially you take the Born sup or the sub-Born of your random variable. So if your random variable is not bounded, that goes to infinity, right? If the alpha goes to infinity, that means that essentially your risk tolerance is very high. It's the same thing as being risk neutral. And these things converges to the expected value of the random variable. Right? So that's something that in economics people have used to look at utility function, and they look at alpha and say, well, what is your alpha? And based on this alpha, I transform any random variable into a deterministic value, and this is how you value that random variable. Okay? Now, we're not going to use it this way. What we are going to use is the following. And this is, well, so that's just an explanation of how it works. You take the exponential of a fixed quantity, that has to be the expected value of that. That's how the certainty equivalent happens for this utility function type. But here is what we are going to look at in terms of parameter that we are interested in. So it's called deadline-based lateness index for a single node. So here we have to think a bit what it means. Right? So now I have a deadline, tau, right? And I'm going to look at a given solution or given random variable, right? And I'm going to try to find the smallest possible alpha right? So this risk tolerance I have, remember, the smallest, if alpha goes to 0, that means you are more and more and more conservative in some sense, right? So I will try to define the value of a path by looking at the smallest possible alpha such that that certainty equivalent is less than or equals to tau. Right? This is how I'm going to evaluate a path. All right? So this is not an alpha that is an individual making. So this is where the leap of understanding here and why does that even matter to do that is important. So do you get what I'm doing here, right? So I take a random variable. I'm evaluating the quality of that random variable as finding the smallest possible alpha such that the certainty equivalent is less than or equals to my deadline. All right? And so in some sense, it's a conservative way of thinking about it. But this is what I'm going to do. I'm going to try to find, so first of all, what is the characteristic of this kind of measure? What does it have nice properties? That's why if it violates monotonicities, if it has all the problems that I had put before, that would not be very good. So you can show that, first of all, that measure that I mentioned, that I repeated here for the sake of referring to, as intuitive things. So first of all, if your random variable by itself is less than or equals to tau, almost surely, that means it's always bounded by tau, then this smallest alpha that you have is 0. Right? Yeah? So again, the smallest, the better. Right? So if you find a random variable, so a path, think about a path, that will be guaranteed to always be arriving on time deadline, then it's a great path. And yes, it's a great path, and its value will be 0. This rho, by the way, is always greater than or equal to 0. Right? So essentially, 0 is holy grail. You would like to have that. If you find a solution that is as 0, this is a great solution. Right? Also, if the path itself, tau, has an expected value that is greater than this deadline, then the rho is infinity, right? So in some sense, if you already have a path where the expected value of that path is greater than the deadline that you have, forget about it, right? So essentially, that means that's a very bad path. So it takes the value of plus infinity. And then you have the third property, which is the important one. If one random variable is dominated by the other one, with respect to the criteria that we have, then you have that property true. So in some sense, you have some kind of a ranking of path according to this criteria. That does not make sense for a decision maker so far. It's just a property associated with the shortest path, or path with this criteria. So we have to parse out a little bit that definition, because this is the one that is really important. If we don't get that, then all the rest after that is not going to be very useful. So let's again look at an example to see how, with a very simple example, this path or this value would behave. So first of all, here you get one random variable that takes two values, 10 and 20, with priority half and half. Right? This one is 14 and 18 with priority 1.5 and 1.5. Right? So what I want to do for all of these two random variables, whenever I get a tau given to me, and I think here I don't know which tau is going to be. Let me just click it. Okay, well, not. So no tau. So I'm going to here define the C, which is this thing here, right? The certainty equivalent curve associated with these random variables. So you will have this curve for this one, right? And the red curve for the other one. So remember what I said before. When you go to alpha going to 0, you are more and more conservative. And if you look at the formula here, and you take it and you do the math, and you take alpha going to 0, you will get to the sup of that random variable. These variables are well behaved, so it goes to 20. So when it's 0, that's why it starts at 20. So it starts at the max here for this one. For the other one, it starts at the max for this one, right? And then it goes down with a given curve like that. And then the limit here, it converges to their expected value. Right? So the expected value of this one is 15. The expected value of this one is 16. So one is 15 here and 16. So this is essentially what the curves are. Right? And now I'm going to use this curve to rank these two paths according to a deadline. It's only according to a deadline that you can evaluate these. So if you take a deadline, for example, of 17, right? Essentially, you want to take a path that would guarantee you, not guarantee, but would ensure that you get close to 17. Then you take that 17 here, right, which is this value, 17. And then, as I said, you evaluate these by taking the nth, right? So you go there, you run there, and up to the point where that blue goes up, that corresponds to the value associated with the first one. Right? This value is the smallest alpha for that random variable to ensure that you have that under. Right? And so you look at the other one. This is this value. And this one is less than this one. I will then choose T2 tilde over T1 tilde. That's all. Right? So this is a criteria that is inspired from whatever. It has nice mathematical properties, and it allows me to rank random variables. Right? So for this case, using this metric, whenever I have random variable like that, I would choose T2 over T1. Now, you can argue whatever. I mean, I prefer T2 or T1. I'm just telling you that this is the selection here. All right? Now, of course, it's not yet another measure, again, for the sake of it. So we want to make sure that whatever silly things that we have seen with the other measures are not here as well here. So I would just want to make sure that I go back here. And remember the previous example, when you take the maximize the probability of arriving on time. When we had this example, that criteria chose T2, right? Now, if you look at the lateness index, it picks T1. The right choose. I cooked the example to make sure that I could. On the other example with the maximize the punctual ratio, again, the model there was picking T2, which was always dominated by this one. At least lateness index takes T1. Right? So these are just illustration and example of why this measure seems to be interesting. Right? Now, if the measure is interesting but is very hard to compute and leads to a problem that is impossible to solve, forget it. Patrick, go back to your working book and do something else, right? So here is what we are going to do. Oh, no, the most important things. I almost forgot. When we started with this problem was not under assumptions about probability distribution. We wanted to look at criteria that could be valid for a class of probability distribution, right? So this is what I call lateness index with ambiguity. Ambiguity is the following. So let's assume you go from A to B, and you have two paths, right? And the only information that you have on the second one is that, which is a full distribution, full. Yeah? So it's all given to you. And the other one is just the range, right? You know that it will never take less than 10 minutes and never than 50, right? And I want a measure that can measure T1 delta as opposed to this one. Why? We realize that, I mean, that's pretty obvious, but if you do things in real world and you want to build, again, the shortest path on a very, very large network where you have GPS data coming at you all the time and you calculate these values, it's extremely good to get, and you assume that there is a probability infrastructure behind it. You don't know exactly what the distribution, but it's very easy to build very good estimator of the mean, of the second mean, maybe a third moment. But getting a lot of data to reconstruct a full distribution, forget it. Right? So what we wanted was something where essentially what we could measure and measure very, very well was maybe the born, 10 and 50. It's pretty easy to do the range. And having a very good estimate of the mean, but nothing else first. What can you say when you have only that? That was the idea. right? So we had to define something, and here, this is what we have defined. You look at the class of, or this is like more theory now. You look at any kind of priority space that you have, that where this P lies in, and you take the sup. So you're still very conservative, right? You are conservative. You want to plan according to all the uncertainty that is there. Now, the uncertainty is not like everything. It lies within some well-known fact that you may have. For example, you look at all the probability distribution that have this kind of support and that kind of mean. That's all, right? So whatever, how you define it, and now you define this, what is called the worst-case certainty equivalence, and now the lateness index associated with that value is the nth of alpha. It's the same thing, but instead of having without the sup, you have the sup, right? And the property that I mentioned before carries through, right? So you can really now start comparing paths or random variables that have very little information about their distribution. Maybe you have their support, maybe you have the mean, and you can really actively compare them according to this criteria. All right? You with me? All right. So now, again, we have shown just an example that this criteria might be good, but the question is that, is it really good? You know, what kind of solution do you get when you want to find really path on a network? So first of all, can you solve this problem? So now what we want to do, I should not move. So what we want to do is the following. Now that we know that somehow this criteria might be interesting, and we know that the lower is the better, this is the formulation that you have. It's a classical formulation. You want to minimize this criteria here. Now, here it's the value associated with a given path, and this is a shortest path type of constraints, right? So it's a classical things that you have learned in your 101 class, right? In shortest path, LP formulation, this is what it is. Here I just formulate it this way, right? So now what we have is that the only thing that is problem is this one, right? This spot here looks fishy. So what we have is that by definition of what it is you can write it this way, right? Now, what I had before was the C alpha F, which was this worst case certainty equivalent associated with one random variable. Here is the sum of random variables. So I'm going to, for the sake of simplicity here, explain just the situation when these random variables, or these networks, correspond to independent. I'm going to assume independence between travel, okay, between link. All papers have always assumed that. That bothers me. I like correlation. We'll talk about correlation at the end, but for the time being, let's assume there is no correlation. Then this property is nice because in that case, by independence, the C of this sum is the sum of this. So it's good. Good property. So the same like, right? It's a nice thing to have. And now we can replace that. You go back to there, and you obtain this formulation. And it turns out that here, so essentially it's a subroutine that you have to solve. And by doing some, I'm not going to go into all details if you want to have information, but essentially it's equivalent to solving a binary search type plus a shortest path algorithm each time. And in the end, what it means is that it's polynomial solvable. So you can solve exactly the optimum solution in polynomial time. Right? So it's on the computational side, hey, that's nice. Now, you have kind of convinced me that it could be a measure that is of interest. It has not, properties that the others do not have. Computationally, you can compute it, but I still don't understand what kind of path it gives me, right? Why would I try? So now this is what we have to do. We have to run experiments, calculate the optimum path according to that, and compare it with other criteria. So this is what we have done. And so here, so essentially it's only on randomly generated graph here, right? Here what I present is a case where you have about 300 nodes, about 1,500 arcs. The distribution on each leaks are called two-point distribution. Essentially that means that you have the lower bound of the arc length, the upper bound, and the mean. Right? That's all what you know, right? And now I'm looking at all these other methods that I talked about. So this one I talked about before. You maximize the arrival probability. This is an NP-hard problem. This is very hard to calculate. There are you cannot calculate on this kind of size of problem. You can never hope to get the optimum solution. So we have used what is classically used in this world, sample average approximation to do that. We'll see that even with these 80 samples, it's terrible. It's a terrible algorithm. It's a terrible thing, but that's the best we could do in the amount of time that we wanted. Here we want to maximize the punctuality ratio, and so here that's from this paper. It's a pretty fancy algorithm using convex optimization, but it's very nice. So we implemented that. Now this one, since I worked with Melvin Sim, and Melvin wrote this paper with Dimitri on robust optimization, and people always, after that, talked about budget of uncertainty and business. We decided to implement their algorithm on the shortest path. So that's called the maximized budget of uncertainty. That's this criteria. It's also solvable in polynomial time for this one, by the way. And then this one, right? And so now, so we have this problem. We have these, and we are going to try to get some. So you might say, well, wait a minute. Here, you need to have the probability distribution in order to do that. Yes, for this one, we give the information. For the others, we don't. Right? So whenever it's needed, like for example this one, we give the benefit of knowing the exact distribution of the sample. And for the others, we don't. Right? So hopefully people say, well, if the true distribution is really the one that is given, that should advantage these things, right? All right, so now here are, so I will go also a bit slow. Wow. Okay, on this data. Okay, so here, how did we, so essentially what we looked at is find solution. When we repeated, there's an average of so many solutions and report, average, the classical thing that you want to make sure that whatever you report is statistically makes sense. But here what we have done is that we have put the solution given by the minimum linearity index as a base factor, and we took the ratio for all the other methods. Okay? Everything that is above 1 is worse, right? And then what we have done is to say, well, these solutions have been obtained using a given criteria. Now we're going to look at this solution, and we're going to do an outsample and test that solution according to many other criteria. What is their mean travel time? What is the probability of arriving late? What is the standard deviation of the path that was obtained by using one of these? What is the EL? EL is expected lateness. That means that now that you are after the deadline, how much more? Here, the conditional expected lateness. Given that you arrive late, what is expected amount of time you're going to be late? And so on and so forth. Here, value at risk, for those of you that know value at risk, it's trivial. For those of you that don't, you have to parse out the definition, and it's more complicated. So forget about these two curves. But so here, so a couple of things. So first of all, the midness index is the worst of all of them in terms of mean. All the other solutions, well, with the exception of this one, but all the other solutions give solutions that on average are faster. The mean is faster. But remember, this is not what we want. We want to arrive on time. Right? So on the other hand, in terms of standard deviation, clearly this is better. In terms of expected lateness, better. Conditional expected lateness, better. And all the others. Now, one thing that is, as soon as I saw this result that were by the students, says, you have to do it all over again. This is totally wrong. How come when you do the maximum arrival probability criteria and you measure that solution that is obtained, that maximizing that, according to the criteria what you minimize, is the worst? Right? Come on, give me a break. You try to find the path that, well, what happened is that the problem is way too big. These solutions that are given here with this sample approximation that we have are terrible solutions. We never reach an optimum solution. So in the end, after that, when we started to test it on much bigger network, we basically gave up that solution because we cannot even compare it. right? So in some sense, this is almost garbage, right? Because in some sense, what you obtain is finding the best path that maximizes the probability of failure on time is hopeless, in addition to having all the problems that we mentioned before, right? So by the way, that was done for, so you have to choose the network and you have to set the networks and the deadline so that it's realistic. If you run a network and then you say, now I'm going to test all my algorithm where the deadline is always less than equals to the expected value of all paths, you're not going to find any feasible solution. So it's not interesting. So you want the deadline to be bigger than at least the expected shortest path, right? So what we have is put a criteria that basically says I'm going to look at my deadline, I'm going to calculate this way. I take the mean shortest path. That means that I look at all my uncertainty set that I have, uncertainty link, I take their mean, I consider that to be the value, and I take the shortest path. Right? So that's what I call the mean shortest path. The worst case mean shortest path is the one you take the upper bound for all the length. Right? So instead of each link, you take their upper bound, and you say this is now the time it takes, and now I'm taking the shortest path on that. And I take a convex combination of these two to define the deadline, to ensure that somehow the deadline is not too strict. Right? And here I have put the value of all these solutions according to this deadline variation. And again, here, this is the lateness index, right? And of course, so again, when the theta here that we have goes to 0, that means that this value here has the highest weight, right? That means the deadline is shorter and shorter and shorter. That means that the set of feasible solution of path that can really meet that is shorter and shorter and shorter. And indeed, most of the solution converge to the same solution. There is essentially one solution possible that every criteria you use, right? So essentially, that's why you get that. But when you allow the deadline to be a little bit bigger, right? The shortest distance is still the shortest distance in terms of expected time. It has a huge variation. And the others at the expense of, so for this one, which is our solution, at the expense of not being as good in terms of mean travel time, is better than all the others in terms of all the ratios, standard deviation, lateness priority. So it's not just one example, right? And we repeated all of that. Yes?
When you're calculating lateness probability, you're assuming that the travel time on each link is either worst case or best case, right?
No. Then after that, when I do the outsample, I put as input the distribution that we use for the method that use distribution. So in some sense, the lateness index is not given the benefit of that distribution to find the solution, but it is tested against the distribution that was used for the other methods. So it's actually, right. So nevertheless, even with that, we are doing very well, right? It would be unfair to the other method, but it would even make sense that you make an assumption about the probability distribution. You use a method that uses a distribution, and the real distribution is not this one, right? So you don't want to do that because already with the true distribution, the others are not good. So, all right. So that was it. That was just one shortest path. That was just one deadline. That can be solved very, very efficiently. What I said about a static problem, we can solve it very, very fast and all the time. So whenever there is a change in the network, every whatever 5 seconds or whatever, and you want to recalculate on a big network, you can do it, right? So it's really, you can use it in real time in some sense. So that was the interest of that method. Now how long do I have? So I'm half my part 1. But so again, the key thing is really this introduction of this new measure. It's not robust in the classical sense. It has some very nice property, and it gives path that looks very good, right? So what we have now this is when Yossiri from Montreal played a role because he had been trained to solve VRP and VRP and VRP, is to look at the more general case where you have now not just one traveler finding the shortest path, but you have a set of M vehicles, right? They might have some capacity, and they have to go and meet some clients. Some of the nodes needs to be visited, some of the others might not need to be visited, and then you have nodes with deadlines, right? So in other words, deadlines, if you want to come and serve me, you have to come before blah, blah, okay? So in order to generalize the framework, you have to introduce a whole new set of index, but they are just an extension of it. So essentially now you have this network, you have more than one node that will have deadlines, so you have to define an alpha for each one of them as opposed to just the time. And somehow you have to combine these in such a way that makes sense. What we have decided to do here is just look at all this alpha that characterize each node. That's the alpha that I had before. And you take the sum of it. It turns out that any convex combination function would work well. But that is already good enough. Try to explain to someone why this criteria works. It works. It mathematically is good. But then introduce a function and say, oh, it can be generalized with a convex function. You give up. People don't even want to hear about it, right? But so that is enough to define our new, what I call composite index, that would evaluate any solution, which is a vehicle routing type of problem, and will give me the value. And again, I want to minimize that thing. Now it's a bit more complicated because the constraints now are VRP. Yeah.
But the alpha is from the beginning of the path all the way to that.
So here, right? So yeah, exactly. So that corresponds to, for example, for this one, right? So if you look at this solution that is given now, it's only one path. That's a simple case. There's only one vehicle that does this trajectory here to arrive here, and this one has a deadline total. The alpha do correspond to that sum, right? And this one, it would be the entire thing up to here, right? So yeah, all right. Yeah. Okay. Now, this is when I'm going to wave my hands. I already waved my hands quite a bit, but here it's just like, you know. So lateness formulation. So we're going to minimize this composite index subject to any kind of VRP constraints, including subtree elimination and capacity. The key thing is really which VRP formulation you want to use, which formulation you want to do a multi-commodity flow type, you want to do that. That is a different matter. We pick the one that is the best in terms of computational aspect. So essentially, this is the formula that you have, right? So here is just the thing that is dealing with this composite index, and all these other constraints that are a pain in the neck. That whenever you go and see VRP people, they just like give you this long list. This is that S belong to S, right? So S has to belong to S, right? So now, to be fair, so what we wanted there, as opposed to the shortest path, if you look at the vehicle routing problem with travel time, and if you look at papers that try to address it, there is, in my view, in travel time, I'm talking uncertainty, not demand uncertainty, travel time uncertainty, there is only one paper that really made some interesting contribution, and it's from someone that you have recently hired. So, so we wanted to deal with this problem and compare to what they had done with the stochastic vehicle routing problem. So here, that's the other formulation, which David Morton did and worked on, and developed, again, sample-based type of approximation to solve it, scenario-based. I think the paper was in 2003. It's in OR. And the largest problem size that you can get is really tiny and with maybe 80 simulation scenarios. But we used our technique just to formulate the problem the same way. This is the objective function and the constraint that he has, and the same set S belonging to S that I had before. Now, the key thing is that there has been a huge progress in technology. Maybe you cannot see that because IP is IP and IP, or Cplex is Cplex is Cplex, or Gurobi is Gurobi is Gurobi. But in terms of cuts, there have been incredible progress on TSP and VRP, right? To a point where you can really solve much bigger instances than before, right? And so this is what we're gonna use all this machinery there. So I promised. So this is the routing set. So it's a bit more complicated. So let's not look at it. But let's look at all this method. And I just want to provide. So how long do I really have? What? Soon? So it's not a lecture that can be extended for 1 hour?
So Patrick, what I'd suggest is find the next convenient break point for you. Then we'll let folks who have a 5 o'clock commitment
Okay.
go, and then we can.
Okay. So bottom line here is that we have implemented this algorithm and we compared it to all these others. It can be solved very fast and it gives very nice results. The paper is available somewhere, right? So if you're interested in that. Now, I want to go quickly to, so this, I will not go through that. I will not go through that. Okay, so part two. Part two, which was the adaptive solutions. So now we're interested is really going beyond what we have done in a static, but we really want to have routing policies. In other words, we are engaged, we are in the network, and what I want is not find my path from Lexington to MIT every morning. I want to know what to do when I'm there at the intersection, and not when I already take the intersection. I don't care if I'm on the highway and Google tells me there is a huge congestion. I know I'm there. If you told me just before I go there, that would be great. So, you know, the timing is perfect. So we have looked at it, and so essentially what we have done also there, in blue is what we have done to algorithm techniques that have been developed. And it goes back to, for example, Bertsekas and Tsitsiklis, very nice paper about this kind of adaptive things. And so we take one step further where we look at uncertainty that is not given as well in a robust version. Okay, so. And also computationally tractable. That's important. But so I'm going to quickly go through that. And there, the conclusion. Always conclude. By the way, for those of you that are on job talks, that's a bad job talks because you don't want to do that. You don't want to run late. You don't want to do that. But that's OK. So here, what I want to highlight is that in terms of generalization of the technique that we have developed. Yes, we can, and these are all either in response to referee that said, well, that's nice, but could you do it more general? No, pain in the neck. But anyway, so travel time uncertainty. So we talked about deadlines only. Now, what happens if you really have time windows? Not only you don't want to be too late, but you want to be too early. Can you extend this lateness index? You cannot call it lateness anymore. So we have, yes, so it's called insatisfactory index. It's way more complicated, but it works. So we can do that. We have done it, and in the same paper, it's essentially the same thing if the uncertainty is not the travel time, but it's the demand. So now you want to serve clients, you don't know how much they want, there's uncertainty. You can use the same kind of technique. And then the key thing is for me, for the shortest path, is that, yes, we can include correlation between arc travel time. In a given way, we cannot have a full correlation, but at least we can incorporate some correlation between successive travel link and still have something that you can compute. Okay? So, sorry, and thank you for your patience.